welcome to our session for physical sciences. My name is Temba. Today we are focusing our attention on resistors in parallel. We want to explore exactly what happens, if you have a circuit whereby you keep on adding resistors in parallel, how exactly that affects, the magnitude of current, how it affects the potential difference, terminal potential difference, and a host of quantities in as far as a parallel circuit is concerned. Now let's locate parallel resistors within the broader, section of electrical circuits. Right. So from our, concept map, we understand that by now, in the context of circuits, right? In the context of circuits, we are saying that, you have got two types of connections. We've got a series circuit, which by now you may recall that it has a lot to do with potential dividers while current remains constant, and exactly what effect does that have if we add more resistors on the current as well as the voltage as well as resistance. But today our focus will be on the parallel circuit. We would want to investigate how that affects the magnitude of current and voltage as well as resistance if we keep on adding resistors in parallel. Right. Now, the thinking that's going to maybe guide our discussion for this session is that think about what exactly happens to the magnitude of current. Okay, we are worried about current in a circuit when more resistors are connected in parallel. All right. Remember, if we talk of a parallel circuit, it's in the context of saying that we've got more than one path for charge to actually flow. So current has got more than one options or alternatives to follow in a complete circuit. That's what parallel means. Okay. Now we want to see how adding parallel resistors in a parallel circuit actually affects the magnitude of current as well as potential difference across each resistor. But for the resistors in this discussion, we would use light bulbs because we know a light bulb is a typical example of a resistor. What makes us say that? We would remember that a resistor is any electrical device or component that actually transforms electrical energy to other forms. So what does a light bulb actually do in a circuit? Much as a circuit is about energy transformation or energy change, what happens when electrical energy reaches a light bulb? The light bulb serves the role of converting that electrical energy into light, and maybe some of it to heat, right? So we would obviously think of a light bulb as an example of a resistor, right? So the second thought is, what happens to the terminal potential difference? That's the voltage, all right? Which is, the voltage, right? What happens to the voltage when more resistors are connected in parallel? So it is essentially about the parallel resistors, right? Okay, these are the keywords, okay? And we've already noticed that, when it comes to definition, it's a all or nothing kind of a situation. It's either you remember the definitions or you don't. So remember again, once more, that the examination guideline serves as our point of reference in as far as the wording keywords that must be used in the correct context is concerned. So as a result, always refer to the exam guidelines for what is acceptable in terms of definitions. Knowing the keywords is not enough. Beyond that, you need to correctly use those keywords in the correct context. So it's either you get 2 marks for defining or you get 0 or 0, right? So it says here, resistor, which is a device. Okay, a resistor is a device, okay, in a circuit. It could be a light bulb, for example, okay? So a light bulb would serve as a perfect example of a resistor for the purpose of today's discussion. And then resistance is the quantity, okay? Now, let's try and remember that when we talk about resistance, we're talking about a quantity, while a resistor is a device that offers resistance in a circuit. And resistance has to do with the opposition of flow of charge or opposition to current in a complete circuit, okay? So a quantity the quantity concerned is resistance, while a resistor, it's a component or a device that will offer a resistance in a circuit, right? So we also remember that equivalent resistance has to do with total resistance. We spoke about this, about, you know, equivalent, sometimes it could be effective resistance. So the word equivalent and effective could be used interchangeably to refer to one and the same thing. Another word or term that we'll use a lot in our discussion is current dividers in the context of parallel circuits, right? Now, we know that resistance is the opposition to the flow of charge. So that's the definition of resistance, okay, as a quantity. So we also know that different components, these are electrical components, that is, they provide varying resistance in a circuit, okay? So an electrical component that has a high magnitude of resistance, okay, will require more energy transfer. Okay, what do we mean by that? Remember, in real life, you know, beyond the theory, we know that we have got many circuits in our everyday life, you know. If you think about the resistance that a light bulb offers compared to the resistance that a heater, which is another appliance or a device that we have in our homes, you know, a heater has got greater resistance. Why? Because the amount of work that a heater does in terms of transforming electrical energy to heat is comparatively greater than that of the light bulb converting electrical energy into light, okay? So that's what we mean when we say different electrical components or devices, appliances, they offer varying, you know, magnitudes of resistance. This is what happens in real life, right? Okay, so an electrical resistance is also measured in ohms. So ohm is the SI unit, okay? R is the symbol for the quantity, okay? While omega, which is a Greek letter from the Greek alphabet, represents ohm. Okay, so when do we have an ohm of electrical resistance? Let's remind ourselves once again. 1 ohm of electrical resistance is actually equals to 1 volt per ampere of current. Okay, so 1 ohm of electrical resistance allows an ampere of current, which is 1 ampere, all right, to pass through, you know, a resistor through which the potential difference is 1 volt that's applied across it. So it takes us back to that mathematical, you know, equation, right? Okay, so resistance, conductors also, you know, in most cases we choose to ignore the resistance that conducting wires offer in a circuit. Hence, we'll say the conducting wires have negligible resistance. Okay, so this term, negligible resistance, is very common in, you know, in our discussion of circuits, because it tells us that, you know, we may ignore the leakage resistance that conducting wires, the ammeter, offers in a circuit. So if they say the battery has negligible resistance, it means that the source does not offer any resistance to the flow of charge. It means all the current passes through the battery. So this is negligible, okay? Okay, negligible, all right? Okay, resistance, okay. So this says to us that the amount of resistance is very low for us to actually ignore it, okay? So how do we calculate resistance? It takes us back, you know, resistance is the ratio of voltage and current in a circuit. It could be the total resistance. If we're talking about the resistance of the entire circuit, we know that the total resistance is equal to the terminal potential difference, which is the total voltage in the circuit, divided by the total current. So this is the total current that goes through the battery versus the voltage of the battery when there is current in the circuit, which is our terminal potential difference. So the notation will vary. Suppose we want to determine total resistance or resistance through a resistor R1. So we'll say R1 is equal to potential difference across R1 divided by the current that goes through R1. So it's just the notation there that you need to take note of, okay? So to measure total resistance, we need to measure the terminal potential difference. So this is what we are talking about, okay? And the total current through the battery, okay? Right, so how do we construct a simple parallel circuit? Okay, what is it that we need? We need a battery, which is the energy source, or a cell, whatever the case may be. We need a conducting material. In terms of physical properties, these are materials that allow charge to flow through them, okay? A resistor, which could be, in this case, we can use a light bulb. It's still fine, okay? Because it's a perfect example of a resistor in a circuit. We need an ammeter for measuring current, okay? To know how much charge passes through a point per second. We need a switch to complete or break the circuit. And then we also need a voltmeter, okay, to measure potential difference across a component. So in ammeter, you remember this is the symbol, while the voltmeter is that, okay? Right, so we're going to set up, you know, a circuit, a simple circuit like the one that you see. And then the question is, how do resistors in parallel affect the flow of charge in a simple circuit? So let's go to our simulation, right? So if we go to our simulation, this is what we have, okay? Now, I'll open that switch for now. You'd realize that there's zero current in this circuit, or there are no charges that are flowing. Why? Because we'll use the conventional current. Why? Because the circuit is broken, okay? But what if we complete the circuit, okay? What if we complete the circuit? There will be current in the circuit, okay? So if we complete, there is our conventional current flowing from the positive terminal to the negative terminal. The reason why there is no current in the other light bulb is because that part of the circuit is broken. So it's not complete because the switch is actually open. Now, what does that 0.9 ampere of current mean? It means that when the first switch is closed, the amount of charge that passes through any point, even through the light bulb, is actually 0.9. It means 0.9 coulombs of charge pass through the light bulb, pass through the battery, passes through the switch per unit time. And when we talk about a unit time, we're actually talking about a second, okay? Now, this is the flow of charge, okay? And that's our total current in the circuit, which is actually the current that passes through the light bulb as well as the battery, which is the source of energy, right? What if then we close the other switch so that the second light bulb becomes part of the circuit? Let's see how that affects the magnitude of current, okay? If we close that switch, you can see now the current is doubled, okay? What does that mean? It means now more charges pass through a point for every second, okay? Now, our initial reading was 0.9 amperes. Now it's 1.8, which is actually double, okay? As you can see, now both light bulbs, let's call the first one light bulb 1, and then the second one light bulb 2. Now, if both of them are connected in parallel, what has happened here? The amount of current that is passing through the battery, or the main current, which is our total current, has doubled because we've added another resistor in parallel. That's the main idea, okay? So if we go back to our slide, the question that we asked ourselves, how do resistors in parallel affect the flow of charge? And what is this flow of charge, okay? In not so many ways, this flow of charge is actually the current in the circuit, okay? This is current in the circuit. Now, by connecting another identical resistor in parallel to light bulb 1, that has actually increased the current flow, okay? Increased actually the flow of charge, okay? Increased, this results in increased flow of charge, okay? So this flow of charge, we've agreed that it's current. In other words, we are saying that connecting more resistors in parallel actually increases the current in the circuit, because we noticed that there is increased flow of charge by adding another identical resistor in series, in parallel rather, okay? So the observation is that when resistors are connected in parallel, the opposition to the flow of charge is decreased. What is this opposition to the flow of charge? So what we have underlined, actually, the term that describes that is actually resistance, okay? So what has happened here, by adding another resistor, identical resistor in parallel, it has increased, you know, the amount of charge that passes through a point, which is the current. But what has that done to the opposition, it means the opposition has become less. So in short, we are saying that adding more resistors increases the current while decreasing the resistance in the parallel circuit. All right, okay. So that's as far as, the first segment and how exactly flow of charge is affected by, having multiple resistors that are actually connected in parallel. So when we come back, we'll explore more about potential difference in current in as far as, a parallel circuit is concerned. Let's take a short breather for now. Welcome back to our second segment. We're still exploring resistors that are connected in parallel. Now let's take a look at a scenario where we investigate the resistance in a circuit where the resistors are connected in parallel, and we want to measure the total resistance of the circuit, okay? And also determine the resistance of each resistor, okay? That's what we do. So we'll go back to our simulation, okay? Now in this case, we will have two resistors, which is a light bulb, okay? The first one will have a resistance of 2 ohms, while the second one has a resistance of 4 ohms, okay? We'll measure the voltage across each of the 2 resistors and then get the total voltage, which is actually our terminal potential difference, okay? When we've got 2 resistors that are connected in parallel, okay? And then determine the amount of current through each resistor to actually arrive at the main current of the circuit. And after that, we'll also determine the ratio of voltage to current, which is our resistance for the total resistance as well as the resistance of each of the 2 resistors. Take note, R1, okay, R1 is light bulb 1 with a resistance of 2 ohms, okay, while R2 is the second light bulb with a resistance of 4 ohms, which is actually double the resistance of R1, okay? So let's go to our simulation and actually check how that works out. So the voltage of the source is 6 volts, okay? So if we measure the voltage of the source while there is no current in the circuit, it will give us an indication of EMF, okay? So our EMF in this case is 6 volts. Now, for this particular discussion, we would assume that the battery offers little or no resistance. So the resistance of the battery is actually negligible. Okay, that's where that term applies in this case. So we are going to close the switch, okay, for both our 2 resistors, okay, which is the light bulb. Let's verify the resistance of R1. The resistance of R1 is 2 ohms, while the resistance of R2 is 4 ohms. So it's safe to say R2 is double R1, or R1 is half R2, whichever way you actually choose to look at, okay? So now let's close the circuit, okay? Complete the circuit and also do the other one, okay? Now, the current that goes through R1 is the 3 amperes, okay? While the current that goes through the R2 is 1.5 amperes, which is actually half, okay? Let us now measure the voltage across R1, okay? Across R1, the voltage is actually 6 volts, okay? So let's go to our table and complete the table. So the voltage across R1 is 6 volts, okay? What about voltage across R2, okay? Across R2, which is the second light bulb, the voltage is also 6 volts, okay? That's what we obtained there, okay? We also have another 6 here, all right? Now let's measure the current that goes through R1 and the current that goes through R2. We have already connected ammeters for each one of those. So the current that goes the first 2 ohm resistor is 3 amperes, okay? And then the one for R2, which is the second light bulb, is half that current, which is 1.5. So if we go back again, so R1 is 3 amperes, and then the other one is 1.5 amperes, right? Now, the total resistance, the voltage in the circuit, we can measure it in terms of the terminal potential difference. So this is V total, okay? if we go back to our table, to our simulation rather, we can measure the terminal potential difference through the source, okay, which is exactly 6 volts, right? So that's our 6 volts that we have there, okay? So this is 6 volts, okay? There's a trend that we are picking up. So this is V1 or V across R1, okay? Now, which is V across R1 is 6, V across R2 is also 6 volts, right? Now, let's look at the main current through the battery, okay? How much current passes through the battery in this circuit, okay? The total current in the circuit that we see that goes through the battery is 4.5 amperes, which is 4.5, okay? Now, if you go back to that table, we get 4.5, okay? 4.5 amperes. So this is our main current, okay? Right? So this is current through R1, okay? Which is that. This is current through R2, which is exactly that. Now, what do we know? We know that resistance, total resistance is equals to total voltage, which is terminal potential difference, divided by the main current, okay? So if we go to our calculator, okay, just to verify that, okay, our total voltage that we recorded is 6 volts, okay? We'll divide 6 volts by the total current in the circuit, which is 4.5 amperes. That gives us 4 over 3, which is, if we change that to a decimal fraction, it gives us 1.33, okay? So this is going to be 1.33 ohms, okay? This is what it is, right? And then for R1, this is what we have. The resistance for R1 is actually V, okay, R1. Instead, we're saying R1, which is the resistance of the first light bulb, is equals to V1 over R1, over I1, okay? The current that goes through that. So it's 6 over 3, which gives us what? The total that we get there is 2 ohms, okay? We get the 2 ohms, which we've already verified. And then if we say 6 over 1.5, we can even verify that from the calculator, okay? 6 divided by 1.5, we get, it gives us a 4 ohms, okay? So this is 4 ohms. There's something very interesting here. So if we go back to that circuit and actually verify the resistance of each one of those, okay, you'd realize that R1 is 2 ohms. We have managed to arrive at that. And then R2 is the 4 ohms, which is exactly the same values that we obtained in the last column, right? But there's something also very interesting here. You realize that the effective resistance, okay, which is the R total in the circuit, which is 1.33. Now, if you think of it, the more resistors we add in parallel, the lesser the effective resistance in the circuit. And our smallest resistor in this case is actually 2 ohms. So the combined effective resistance of the 2 ohms and the 4 ohms connected in parallel must be less than the smallest resistor. The smallest resistor is 2 ohms. And then the total resistance of those 2 connected in parallel is less than 2, which is 1.33. It makes a lot of sense. So the main point where we started, we said as we add more resistors in parallel, what happens to the opposition of the flow of charge? The opposition decreases. So why does it decrease? Because there is now more current. We have seen that the flow of charge increases when we add more resistors in parallel. Right. So that was the main idea in as far as this one. So that's the circuit that we used, okay? We've managed to measure our voltage across each one of those. So it makes a lot of sense, okay? So we've verified this is our R total, okay? Right, okay? Then that's the main current, which is the current total, okay? And then this is our V total, which is our terminal potential difference, okay? Right, and then if we move further beyond that, okay, we've verified again that R1 is actually equals to 2 ohms. And the 2 ohms comes from, V1 of 6 divided by, I1, which is the current that goes through, the first light bulb, Okay, so the other one is obviously amperes because it's current. Take note of that. Okay, right. So if we step off that, we realize that the voltage, there's something very special about the issue of voltage. Check the voltage in the circuit, which is parallel. There is a pattern or a trend that we kind of pick up there. We are saying that V total is equals to V1, okay, which is equals to what? V2, okay. The trend is such that no matter how many resistors we connect in parallel, the potential difference across each one of those would be equal to the terminal potential difference. So this takes us to the main point that we want to also try and arrive at, to say, okay, if we are to investigate the resistance in a circuit where resistors are connected in parallel, we are able to measure the total resistance of the circuit using R total is equals to V total over I total, right? Okay, so this is actually the terminal potential difference. Take note of that, okay? That's the terminal potential difference, okay, of the circuit. And then across each resistor, let's say for argument's sake, R1, okay? You have to find the voltage across R1 and how much current flows through each one of those. That's why we were able to get, verify the 2 ohms as well as the 4 ohms that we actually set it up in our simple circuit, which was parallel. Okay. Now, in an investigation of resistance in a circuit where resistors are connected in parallel, what is it that we observe? We observe that the total resistance, that's our RT, okay, of the circuit is less than the resistance of either of the resistors. So the smallest resistor was R1, okay, which was 2 ohms, okay, while R2 was double that, which is 4 ohms. Now, the effective resistance must be smaller than R1, which is the smallest resistor. So adding more resistors effectively decreases the total resistance of the circuit. Hence, we are saying that there is lesser opposition to the flow of charge, okay? So the relationship between equivalent resistance in a parallel circuit is not the same as in a series. But where does this take us? As we add more resistors in parallel, there is lesser total resistance. While in a series, by comparison, we said as we add more resistors in series, there is greater opposition. So there is greater resistance in adding resistors in series compared to adding resistors in parallel, which effectively decreases the total resistance of the circuit, right? Okay. Now, having said that, there are some aspects that you also need to think about. We used an example where the 2 resistors were not identical. Even if the resistors were identical, say for argument's sake, instead of having the 2 ohms and the 4 ohms, we have a 2 ohm and another 2 ohm. If we check the effective resistance, still it will decrease as we add more resistors in parallel. Okay, having said that, let's look at our simulation. Okay, this is what we're going to do. We'll change the resistance of R1. In this case, it was 2 ohms. Let's make it 4 ohms so that these 2 resistors, they become identical, okay? Now, if you realize that if there are 2 resistors that are connected in parallel, okay, the effective resistance in the circuit will be less than 4. So no matter whether the resistors are identical or not, as we add more resistors in parallel, that will effectively decrease the resistance in the circuit, which explains why we get even more current. So if, say for argument's sake, we have got that resistor, only R1 at a point, okay? Because it's alone, it is in series. What if we add another, because this is a 4 ohm resistor, and R2 is another 4 ohm resistor. So if we add another 4 ohm resistor, you can see that this is the total current that we have in the circuit, which is 1,5. What if we add another 4 ohm resistor in parallel? You realize that the current doubles. What does that mean? It says to us that adding the other 4 ohm resistor, which is identical, effectively decreases the total resistance in the circuit. So for us to actually measure the resistance of the whole circuit, we must measure the terminal potential difference, okay, which in this case is 6 volts. And then we also know the total current through the battery, which is the 3 amperes. So if combined, resistance in this case becomes the combination of those two. So if we can say, okay, R, okay, total, that's what we're looking for, right? So, but we've got V total, okay? The V total that we have in this case, just to verify that from the circuit, is 6 volts, okay? We're given that we have measured that, it's actually 6 volts, okay? Now, the total current that goes through the battery, in this case, what does it give us? We've got 3 amperes of current. So if we've got 3 amperes of current, okay, and we want the total resistance in the circuit, we can have, in this case, you know, R total, that's what we're looking for, is equals to V total divided by I total, okay? So R total, which is the effective resistance of the 2 identical resistors, is equals to 6 divided by 3, which gives us, you know, the 2 ohms. So if R1 is equals to 4 ohms and R2 is equals to 4 ohms, their effective resistance is actually 2 ohms. So adding more resistors, we can arrive at that conclusion that it actually reduces the opposition to the flow of charge. But what has that done to the total current? The total current is increased from 1.5 to 3 amperes. So it means it has doubled. That's the main, you know, point that we want to actually get across. So in as far as a parallel circuit, this is what we have to take home for now, that as we add more resistors in parallel, you know, there is an increase in the current because there is lesser opposition to the flow of charge. That effectively decreases the resistance of the circuit. So as a result of it decreasing resistance in a parallel circuit, there is greater current. That's the main point that we have to kind of get our head around it, okay? So after the break, we'll explore more in terms of potential difference as well as current in a parallel circuit. Let's take a short break for now. Welcome back to our third and final segment. We're still discussing resistors in parallel. Now we want to verify, you know, some of the results that we managed to get, and we've used those findings to actually predict, to say, okay, what exactly happens if we add even more resistors in parallel? What happens to the effective resistance in the circuit? Also, how does that in turn affect, you know, the main current in the circuit? But beyond that, we also want to look at the 2 resistors, you know, which are not identical. We'll have one of 2 ohms and another of 4 ohms. Obviously, the 4 ohm is double the 2 ohms, and also want to look at the current issue between those two, as well as the potential difference across, you know, the source and across each one of the 2 resistors, R1 and R2. Right, so we want to examine the results as well. It says here, in a parallel circuit, what do you notice about the potential difference, which is the voltage, right? The potential difference, which is actually the voltage, okay? So what do you notice about the potential difference, which is the voltage, okay? Or across the resistors. Now we want to look at the voltage across each one of the 2 resistors. Now we are saying that R1 is equals to 2 ohms, okay? And then our second resistor that will connect in parallel is equals to 4 ohms, okay? Take note that R2 is equals to 2 times R1, or R1 is actually equals to a half of what? Of R2. We are simply saying that take note of that, you know, proportion between those 2 resistors, right? Okay, so we'll go to our circuit, we'll use a 6-volt battery whose resistance is negligible. And what does that mean? It tells us that all the current you know, passes through the battery, and the battery actually, as the source of energy, does not provide any or offer any, you know, opposition to the flow of charge or to the current in the circuit. Then we would measure the voltage across the battery, which is our terminal potential difference, and across R1 and R2, right? Okay, so if we go to our simulation, okay, so we have our voltage across the battery while there is no current. Just to verify that as well, it's actually equals to 6 volts. So even because we are saying that this battery does not offer any opposition to the current or to the flow of charge, then we would ignore its resistance. Hence, we would describe that in terms of the battery having negligible resistance. Okay, so if we close the switch, okay, current starts to flow. Okay, but remember we need to have two light bulbs or resistors connected in parallel. So our R1, its resistance is 2 ohms, which is half that of R2, which is 4 ohms. Okay, so now we want to measure the potential difference across each one of them. The current readings are already shown by the ammeters connected, for the current that goes through R1 and that which goes through R2. So if we look at the voltage across R1, it's exactly 6 volts, okay, which is the same or equal to that of terminal potential difference. Take note of that. Then how about the voltage across R2? R2 is double R1, okay? So R2 is 4 ohms, okay? And then the voltage across, or the potential difference across R2 is also equal to 6 volts. That's what we take note of. But also pay attention to the current. The main current through the battery is 4.5 amperes, while across through R1 is 3 amperes, okay? While that which goes through R2 is 1.5 amperes, okay? So that's as far as the measurements are concerned, okay? Now, we said that the R total, okay, V total rather, is equals to 6 volts, okay? All right? And then we know that V across R1, okay, is also equals to 6 volts, okay? V across R2 is also equals to what? 6 volts. But also there's something about current. The main current through the battery which is that current, okay? The total current is 4.5 amperes, okay? Current through, R1, which is current through R1 is equals to 3 amperes, okay? While the current through R2, okay, is equals to half that, which is 1.5 amperes. So that's as far as the data that we need in as far as, analyzing these results, okay? So, okay, this is what it is. The total voltage was 6 volts, okay? And we also saw that the voltage across R1 is equals to the voltage across R2, as we have shown here, okay? Right, so this takes us to the fact that V total is actually equals to V across R1, which is also equals to V across R2. Right, that's an interesting observation in as far as potential difference. All right, what about the current? Okay, current main, which is that 4.5 amperes, is equals to the sum of the current through R1 plus the current through R2. Okay, but take note, the current through R1 is actually double the current that is through R2, okay? And the main reason is because of R1. R1 is 2 ohms, while R2 is 4 ohms. So for 4 ohms, what that simply says to us is that R2 actually provides a greater opposition to the flow of charge, okay, which is high resistance, okay? Now, R1, which is 2 ohms, which is less than the 4 ohms, okay? What does that say to us? R2 offers or provides, lesser opposition to the flow of charge. Hence, it has a lower resistance. That's why if there is a lesser opposition to the flow of charge, there is more current because the opposition is actually lesser by comparison, okay? So that's a very important observation. Okay, where does this lead us in terms of the conclusions? When resistors are connected in parallel, okay, we know that the voltage remains constant. That's the main thing. We've already proved or verified that fact, okay? So in a parallel circuit, voltage remains constant. So the terminal potential difference is equal to the potential difference across R1 is also equals to the terminal potential, it's also equals to the voltage across R2. Hence, we say the voltage does not change as long as it is in a parallel circuit, right? Okay. Furthermore, okay, in a parallel circuit, let's think about what do you notice about the current in the circuit. Okay, if we can go back to that circuit, the one that we managed to get the figures. Okay, so the total current, which is that, okay, so the total current, which is actually equal to 4,5 amperes, that's our total current, okay? Now, that total current is split between R1, which is 3 amperes, and R2, which is 1,5. So if you add those two, they actually give you the total, current in the circuit, right? Now, if we also look at the middle column, which is about the current, so our total, which is 4,5 amperes, okay, is equals to, the 3 amperes plus the 1.5. And take note, R1 is less than R2, okay? Because R1 is less than R2, or R1 is equals to half R2, okay? This is another fact, okay? So where there is greater opposition to the flow of charge, there is actually greater resistance. So hence we have got lesser current in R2 than in R1, okay? So that's a very, very important observation from the data that we managed to obtain, okay? So we've also managed to measure the current, okay, from that goes through each one of those versus the main current that goes through the battery. So in short, we are saying that the main current through the battery is the sum of the current that goes through bulb number 1 and the current that goes through bulb number 2. Okay, so this is the main thing about this parallel circuit that we've just explored. Okay, and if you add the 3 and the 1.5, it gives you that total current, which is the main current in the circuit. Right. Okay. Right. So what conclusions can we arrive with regards to current in a parallel circuit? What do we know? The current is divided in a parallel circuit. So the total current is split between a number of resistors connected in parallel. Let's say, for argument's sake, okay, to generalize this, if we've got an n number of resistors that are connected in parallel, the total current will be split between those n resistors. So if you say current through R1 plus current through R2 plus current through Rn, it must give you the total current for those n resistors that are connected in parallel. Hence, mathematically, we arrive at this conclusion in as far as the total current being divided. But also, the largest current passes through the resistor with the smallest resistance. That's a very, very important, implication. Now, you realize that the 2 ohm had 3 amperes of current passing through it compared to the 4 ohm, okay, which had half that current, which is 1.5. So in short, what are we saying? The greater the resistance, the greater the opposition of flow of charge. Hence, we've got less current where there is greater resistance in a parallel circuit. And conversely, we are also saying, in a different way, that the resistor that has got the smallest resistance in the parallel combination will have the greatest current passing through it. Why is that so? Because we are saying that the smaller the opposition to the flow of charge, the greater the flow of charge, because there's actually lesser resistance. That's the main thing about the current. Okay, right. We've realized that the current through R1 is greater compared to that of R2, because R2 is twice R1. All right, okay. And then we also recall that resistance uses that equation. So it means for the same potential difference, the greater the resistance, okay, the smaller the current. So you need to understand that mathematical relationship as well, okay? Now, having said that, so for resistors in parallel, this is what we also notice, that for us to get the total resistance, we would actually consider the reciprocal of each resistor as a sum. But remember, this equation actually gives us the reciprocal of the total resistance in parallel. But we are actually looking for Rp at the end of the day, okay? Right, and then in summary, we understand that opposition to the flow of charge is actually the resistance, okay, of a component or a circuit. And the SI unit, which is the ohm, is actually equals to a volt per ampere, right? That's the main idea in as far as our parallel resistors are concerned. So the long and short of it says, in a parallel circuit, current is divided, okay, while potential difference remains constant. And then this is how the equation that we would use to determine the total resistance in a parallel circuit for n resistors connected, for n resistors that are connected in parallel. Right. So you know, after all's been said and done, the main idea that we want to get across is that in any parallel circuit, the effective resistance, as we add more resistors in parallel, the effective resistance will decrease. And in the process, current is going to increase. That's the time that we had for today, just to look over the concepts around, or exploring the concept around, you know, parallel resistors. From myself, Themba Ncube, bye-bye for now.